Okay, if you've ever been that person woken up by a security alert at like 3 a.m., or maybe your day job is just keeping a massive code base patched, well, you'll know this problem instantly. The sources we looked at this week, they call it an unwinnable race.
That's a good way to put it, yeah. Vulnerabilities, they just keep getting found and reported way faster than human teams can possibly keep up. The whole triage, reproduce, fix cycle,
Right.
it's just overwhelmed.
Exactly, and that leads to these huge patch backlogs, right? The clock's always ticking, which means high stress, engineers pulled in a million directions.
And risk windows that just stretch out for weeks, sometimes longer, while someone manually tries to figure out a fix, get it reviewed. It's not just slow. Honestly, it's
Yeah.
kind of demoralizing for the
Release.
teams involved.
Yeah, I can imagine. And that's really why we wanted to do this deep dive today. We're going to unpack Google CodeMender. This is an AI agent, and the idea is that it could fundamentally rewrite the rules for code security.
It's not just spotting the problems, the red flags. The claim is it can propose fixes, test them, and actually land them automatically.
So our mission today is basically to get into what this system actually is, how it works.
Yeah, the tech underneath it all, and maybe more importantly, what it could mean, strategically for security going forward. I mean, the big goal here seems to be shipping safer code faster.
Right, and getting engineers away from that constant vulnerability whack-a-mole and back to building features.
Hopefully reclaiming some of that valuable time.
Okay, let's dive in. Let's see if we can finally win this race. Hashtag tag tag one, the unwinnable race and the bottleneck. So to really get why a system like CodeMender might be needed, we have to look at why we're losing the race now. I mean, security tooling, it's gotten incredibly good at discovery, hasn't it?
Oh, absolutely. We've got amazing fuzzers just hammering systems with inputs, static analyzers finding risky patterns, CI/CD pipelines scale that discovery part beautifully.
Where's the breakdown if we're so good at finding things?
Well, it breaks down right at the human handover point.
Yeah.
That's the bottleneck. Discovery scales, maybe linearly, maybe even exponentially sometimes, but the repair, fixing the bugs, that's still very manual,
Right.
artisanal, as one source put it.
Artisanal patching. I like that.
Uh-huh.
So that handoff is where it all slows down.
Totally. It takes the deep knowledge of the code. You have
Yeah.
to carefully thread the logic, test it painstakingly. Look, spotting a heap overflow might be relatively quick with the right tools, but crafting that surgical minimal fix,
Yeah.
proving it's correct with tests, getting it approved, getting it upstreamed before an attacker turns it into a weapon, that's the hard part. That's the bottleneck.
So engineering teams are basically drowning in alerts because we've scaled up the finding part, but not the fixing part.
Precisely. And that leads to burnout, context switching, which ironically probably leads to more mistakes.
Yeah.
CodeMender is aimed squarely at that specific pain point. The idea is to shift the bottleneck. Instead of relying on that tired engineer, bleary-eyed, looking at logs at 3 a.m.,
We've all been there.
you shift it to automated, really rigorous validation. It takes the report, finds the root cause, drafts a patch, tests it against all sorts of evidence. So the human is reviewing trusted output, hopefully, not starting the whole painful process from scratch.
Okay, but if the patch is fully automated, what's the biggest remaining risk? What still needs human eyes? And how does CodeMender try to minimize that?
Yeah, good question. The biggest risk is always regression.
Right.
You fix one thing, but you accidentally break 10 other things. Or maybe the fix works, but tanks performance. CodeMender tries to minimize this with its internal validation loops. They're designed to be more rigorous, frankly, than a human reviewer often has time for. It requires itself to pass all the existing unit tests, plus it often generates new tests like property tests to confirm the vulnerability is actually closed without changing other baseline behaviors. Hashtag tag2, CodeMender's 2 modes of defense.
Interesting. The sources talk about it almost like a teammate with 2 different jobs, or 2 modes. One cleans up immediate messes, the other prevents future ones.
Exactly. That dual approach is pretty critical for software security.
Yeah.
You need both. You need the reactive firefighter, but you also need the proactive structural engineer, maybe.
Okay, let's look at the firefighter mode first, the reactive side.
Right, that's the reactive defense. So
Gotcha.
a 0-day drops, or maybe just a fresh vulnerability report comes in, CodeMender is designed to act fast. It tries to reproduce the issue in its sandbox, analyzes the trace, figures out what's going on, and then proposes a really surgical minimal patch.
Minimal is key there.
Very key. The focus is on small, targeted edits, not huge refactors. Why? Because that significantly shrinks the risk window. Small changes get reviewed and merged faster, less friction.
Makes sense. And then the proactive side? That sounds like where the real long-term leverage might be.
That's the proactive defense mode.
Yeah.
Yeah, this is about systemic improvement. Here, the agent scans the whole code base, looking for entire classes of bugs, not just one instance. It hunts for those known insecure patterns or brittle idioms.
Like what, for example?
Like swapping out unchecked C-style arrays for safer bounds-checked container types, maybe. The goal is to sort of raise the floor for security, making common mistakes literally impossible to compile in the first place.
Okay, that's a pretty big claim, fixing whole classes of bugs before they're even reported. We see a lot of AI coding tools making promises, but the sources give some actual numbers here. This isn't just working on small test projects, right?
No, not according to the reports. The early track record they cite is actually quite compelling. Apparently, CodeMender has already upstreamed 72 security fixes into major open source projects.
Wow.
Yeah, in just 6 months. And we're talking big, complex, multi-million line code bases, things like parts of the Linux ecosystem, popular image libraries. So it suggests this isn't just a proof of concept. It's actually engaging with real-world code complexity and, crucially, the human governance side of open source.
All right, let's shift gears a bit and look under the hood. What's actually powering this? The sources mention the Gemini Deep Think engine, but they emphasize it's not just a chatbot guessing code.
Right. That's a crucial distinction. The Gemini engine provides the core reasoning ability, the intelligence to understand the semantics of the vulnerability report and the code itself. But look, in security, raw intelligence isn't enough. It absolutely has to be grounded in hard evidence.
Okay, so how does it avoid just hallucinating fixes like some generative models might? How does it stay grounded? What tools does it use?
It uses a pretty rigorous multimodal tool stack. So it's not just reading text. It uses static analysis to reason about, control flow, data flow. It uses dynamic analysis, actually running the code in a sandbox to observe its behavior. It uses fuzzing to generate more inputs, try to find edge cases, and critically, it uses SMT-backed checks.
Okay, SMT-backed checks. Can you break that down quickly? Sounds technical.
Yeah, think of them like formal methods, almost mathematical proof systems for code. A simple unit test checks one example, right? Does input A give output B? SMT checks let the agent try to prove certain properties hold true for all possible inputs or under specific conditions, like proving this memory boundary will never be crossed.
Ah, okay. That's a much stronger guarantee than just testing a few examples.
Exactly. So by coupling its reasoning from Gemini with these grounded signals, the static analysis, the dynamic runs, the SMT proofs, it only proposes a patch when its automated validators give the green light. Checks for correctness, checks for regressions, even checks for coding style.
So Gemini provides the deep understanding, the initial spark maybe, but the actual security work, the process, is structured more like a team effort. The sources called it a multi-agent system.
It is, yeah. Security remediation, fixing things. Yeah. It is a team sport in the real world, and this structure kind of mirrors that. You've got the first agent, the scout. Its job is to pinpoint the defect, localize it based on the trace or record.
Okay.
Then you have the builder.
Yeah.
That agent actually drafts the patch, trying to keep it minimal and surgical, like we talked about.
And then the third one, the critic. That sounds important.
Oh, it's absolutely essential. The critic acts as the automated peer reviewer. It's tough. It takes the builder's proposed patch and just scrutinizes it intensely.
Yeah.
Compares the behavior of the patch code versus the original, runs all the tests, especially looking for those semantic regressions or performance hits.
So it's like an internal quality gate.
Precisely. If the critic finds any flaw, it basically rejects the patch and sends the builder back to the drawing board. And it demands an explanation, too, making sure the fix addresses the root cause, not just papering over a symptom. That internal pressure loop is what's supposed to ensure high-quality patches that can actually earn the trust of human maintainers.
Okay, let's make this more concrete. Stories often work better than just descriptions. The sources gave a couple of real-world examples.
Yeah, the first one was a good illustration of that root cause analysis idea. So a report comes in classic heap overflow. That's the symptom, right? The crash.
Yeah.
A quick human fix might just slap a bounds check right there at the crash site, try to stop the bleeding.
But CodeMender didn't stop there.
No. It traced the data flow back up the chain.
Yeah.
And it found the overflow wasn't just a local mistake. It was actually a symptom of a deeper systemic problem, a broken stack discipline logic inside a complex XML parser. It was mismanaging nested elements way earlier.
Ah, so the overflow was just the final consequence.
Exactly. So the agent's fix wasn't just a Band-Aid at the crash site. It repaired the fundamental stack handling logic, and it added a new property test to ensure the parser respects its own rules, its invariants, from now on. It fixed the underlying design flaw, not just that one instance.
That really is a shift from just triaging to thinking about sister design. Okay, the second example, the proactive rewriting one. This really highlights that idea of deleting whole bug classes before they bite you.
Absolutely. This is in a popular image processing library. The agent went through and proactively refactored hundreds of places in the code. It annotated critical code paths with newer compiler-enforced bounds, safety features. It swapped out older utility functions for versions that only accept safer checked data types.
So this isn't a runtime fix, it's changing the code so that errors can't happen.
It's a build time fix, mostly. That's the power of it.
So how does that actually translate into saving time for the people maintaining that library? What's the payoff?
The payoff is trading potentially many late-night firefighting sessions for one, albeit possibly large, upfront systemic refactoring effort. The really profound effect is that entire categories of memory corruption bugs that used to require complex runtime debugging, they just fail to compile now. They won't even build.
Wow.
The compiler itself becomes your first and maybe most aggressive line of defense, catching mistakes the moment a developer types them. Think of the thousands of hours potentially saved chasing down bugs that, after the refactor, simply cannot exist in the codebase anymore. Hashtag tag 5. The compact playbook and guardrails.
Okay, this focus on rigor, on evidence, on systemic fixes, it gives us a kind of playbook, doesn't it? For you listening, even if you don't have CodeMender today, what are the core lessons, the philosophy we can maybe start applying right now?
Yeah, I think there's a definite philosophy emerging from how CodeMender operates, focused on trust and reducing friction. First principle seems to be, start with evidence. Always. Capture those crash inputs, the logs, the failing tests. Treat them as first-class artifacts, ready to feed into any workflow, automated or human. Good evidence just makes debugging faster and patching way more precise.
Okay, evidence first. And the second point sounds like it tackles that human review bottleneck we talked about earlier.
It does. Optimize for small changes. CodeMender is deliberately tuned to create the smallest possible diff that securely closes the vulnerability. Why? Because small diffs are just fundamentally easier and faster for humans to review. It lowers the cognitive load.
Right.
That speeds up the whole deployment pipeline and makes it less likely reviewers will miss something subtle in a huge, complex patch.
Makes sense. And the third point is about making fixes stick, preventing regressions.
Exactly. Add property tests. When you find a bug, especially one that breaks some fundamental rule or invariant the system was supposed to follow, you must encode that rule into a test. That way, the same mistake can't just creep back in later wearing a slightly different disguise.
Okay, evidence, small changes, property tests, and the last one.
And finally, remember, accountability matters. Keep humans in the loop. The vision here is agents draft and validate. They do the heavy lifting. But human maintainers must remain the final approvers. That preserves accountability, ownership, and ultimately trust in the process.
Right. Automating something this powerful, you absolutely need safety mechanisms, you need guardrails. What were the non-negotiables the sources mentioned? The three absolute requirements for using these kinds of systems responsibly.
Yeah, the sources were really clear on this. Three main guardrails. One, log everything, every prompt, every generated patch, every test run. All the validator outputs keep a full, transparent audit trail. No black boxes. Two, gate on tests. This is like the prime directive. No patch gets shipped, period, unless it passes all the relevant unit tests, integration tests, and those property tests proving the fix. If the tests aren't there, the system should ideally be directed to write the tests first.
Test-driven security, almost.
Kind of, yeah. And three, respect maintainers. The AI is there to reduce toil, to help. It should never bypass the established code owners or their review processes. Trust is paramount. Hashtag 6, strategy and availability.
So where does CodeMender actually stand today? It sounds like it's being used internally at Google, maybe focused on some external projects, but it's not like generally available software you can just download yet.
That seems to be the situation, yes. It's described as being within a research pipeline. Every single patch it drafts still goes through all those automated checks and then lands in a queue for human review and final approval. No automatic merges bypassing humans right now. The current focus appears to be on demonstrating its reliability and building that crucial credibility by shipping genuinely useful, accepted fixes to important open source projects, proving it works in the real world.
Okay, so if we zoom out, connect this to the bigger industry picture, what's the really significant strategic shift that something like CodeMender represents?
I think the shift is pretty fundamental. Look, we've spent, decades getting really good at scaling discovery. Better scanners, fuzzers, SAST, DAST, all that stuff. And that era gave us Frankly, mountains of findings, often more than we could handle.
The unwinnable race we started with?
Exactly. The strategic message here, the potential shift, is that the next decade might belong to scaling repair. CodeMender is presented as evidence, maybe early evidence, that we can now apply the same kind of automation and rigor to fixing vulnerabilities that we previously applied only to finding them. It shifts the whole defensive focus towards being more proactive, making fixes measurable, and hopefully making security more of a shared automated effort. #outro.
So, reflecting on this deep dive, it really seems like the core message is attackers automate relentlessly, and defense has to automate too if we want to keep up. A system like this aims to give engineers significant leverage, compressing that time from bug report to safe deployed code, maybe even erasing whole classes of mistakes before they happen.
Right. And maybe a final thought for you listening. If you want to prepare your own code base, your own environment, for a future where agents like this might plug in and help, you can actually start now by adopting the philosophy. You don't need the AI agent yet. Pick a module in your system today that you know is brittle or causes problems. Go write those property tests you wish you had last time it broke. Maybe start a small, proactive sweep yourself to refactor a known dangerous pattern.
So, get your house in order, basically.
Yeah. Optimize your own workflow for evidence, for small patches, for strong tests now. That way, when this level of automated repair becomes more common, your systems and processes will already be ready to take advantage of it. You'll be ahead of the game.
Fantastic advice. That's all the time we have for this deep dive. Thanks for joining us.
My pleasure.
We'll catch you next time.